Hello, everybody. Good afternoon. Welcome to the Statistical Foundation for Reinforcement Learning. This is our 13th lecture, and today we're going to continue to talk about the offline reinforcement learning and focusing on off-policy evaluation. Okay, so homework 2 is supposed to be due today. Though I am behind schedule on grading homework 0 and homework 1. So yeah, if you are you need like a week or two, or like so I've reset the grade scope so that you will be able to submit all homework until the end of the quarter. Right, so there will be there will be no penalty for late submission of the homework. So you should take your time to do that. And meanwhile, like when I got some time to breathe on my schedule, then I'll go and grade the first two homework. So you guys receive some feedback from me. Like another thing is on the project midterm checkpoint, and thank you guys for submitting the midterm milestone. I haven't managed to gone over them, but I'll make sure that I do that like latest by Wednesday. Yeah, sorry for the delay because this quarter has been really hectic with a lot of activities going on. Yeah, I hope you guys can understand. All right, so today let's talk about off-policy evaluation a little bit more in the setting of reinforcement learning. So that's a quick recap. So the problem setup is the following. So off-policy evaluation is one of the two problems in offline reinforcement learning. The idea is that someone gives you a policy pi, and all you want to do is to evaluate this policy pi by estimating how well it is performing. Like suppose it was this policy that was wrong in the past, and using the data that had been collected by a different policy. So previously the offline trajectories. So these are the sequence of interactions with the environment collected by running a different policy called login policy, login policy mu, and you want to evaluate the new policy pi, right? So today we're going to focus on task 1. And in the last lecture, we talked about offline policy evaluation under simpler models. Specifically, we talked about the contextual bandit model, and in some cases, we even restricted ourselves to consider the multi-arm bandit problem, when the only thing that is not degenerate to a singleton is a number of actions, is a finite number. And in the contextual bandit case, the setting is that the state variable is join IID, so your actions isn't affecting the distribution of the future state that you receive. So both of these two settings are simpler versions of reinforcement learning that had a lot of practical applications. So in our discussion on in contextual bandits, we talk about many different ideas of constructing such an estimator. So we talked about the direct method, which is about fitting a regression model from state and action to some real value, and then plugging. Yeah. So in this case, the state are IID, so we can average over the observed state, and then plug in the target policy pi's choice at this particular state, and just average everything, right? So suppose this R hat converges to the true expected reward function, then this is a consistent estimator. But that's a big assumption to make. And the second idea that's a second idea that was independent to this and doesn't rely on such realizability assumption and consistent assumption of this regression estimator is called importance sampling. So importance sampling essentially reweights the observed rewards by dividing the probability that the action was taken by the login policy and multiply that with a probability that supposedly this target policy would have taken this action, right? So by doing this reweighting, the importance sampling estimator is unbiased. Though when the logging policy and the target policy are very different, then it could suffer from high variance. And then we talk about ways to reduce the variance. In particular, instead of dividing, simply taking the average by dividing by n, we can now dividing by the sum of the weights, so which gives us a self-normalized or weighted importance sampling. We also talk about combining the idea of having a regression estimator and the importance sampling, basically the idea is that let's use this regression estimator as a baseline, and then we can try to use importance sampling idea to debias this baseline, right? And then use it to estimate the bias of the regression estimator, which makes the algorithm the estimator unbiased, just like IS. But then you can also take into account the benefit of having some best effort style like supervised learning model that you can build, right? And then lastly, we talk about switch, which is yet another idea for us to incorporate the one given regression estimator. So this is about, well, since the high variance is coming from the importance weight and we can actually observe the importance weight, let's switch back and forth between using the importance sampling or using the regression estimator. And when the importance weights are relatively small, then let's opt on the for the more conservative approach that we do not rely on assumptions. So we'll use importance sampling there. And when the importance weight, like we denote it with rho, which the importance weight is pi of a given s over mu of a given s. When this is large, then we will like switch to the regression estimator. Yeah, to opt for a low variance, even though that introduces some bias. Okay, so one of the interesting things that we discussed last time was that in the multi-arm bandit setting, the direct methods and the importance sampling estimator, they are actually very closely related to each other. In fact, the direct method can be written as an importance sampling form with like the only difference is that instead of using pi over mu, when both pi and mu are their true value, it suffices to replace this mu with mu hat, and then the importance sampling objective recovers the direct method approach, at least in the multi-arm bandit case. We showed that like asymptotically, as the number of data point goes to infinity, in multi-arm bandit, the direct method is always a better estimator in the sense that the bias goes to zero like exponentially, and the variance is much smaller than the importance sampling estimator. So in this case, DM is in some sense asymptotically efficient, meaning that it cannot be beaten by any other estimator. But like in a finite sample, when the number of actions are large, then it is better to use the importance sampling approach. Yeah, so which estimator is better really depends on like the regime and the setting that you're operating in. Okay, so that was what we covered last time. And yeah, these are like the two approaches that we talked about. We'll be deriving versions of this for the reinforcement learning setting today. Yeah, we talk about yeah, doubly robust estimation and switch. Okay, so in today's lecture, we'll be generalizing these ideas to the reinforcement learning setting, and then focus on the focus on the finite horizon episodic the finite horizon episodic case that we talked about a couple of lectures ago. Now, the model that we will assume is finite horizon MDPs with a finite state, yeah, in most of the time we consider finite actions, but I'll also discuss what happens when this actions is not finite. But in today's lecture, we'll always assume the states are finite. So we'll talk about the impact of a long horizon. So which makes the problem substantially harder and makes the generalization of the aforementioned, say, important sampling technique suffering from a huge, actually exponentially large variance as a function of the horizon. And I'll talk about the ways to mitigate this through so-called marginalized importance sampling an intern of mine and I studied a couple of years ago. Okay, so let's start by like rewriting the importance sampling estimator for the reinforcement learning setting. Okay, so what is the data that we collect? So again, in reinforcement learning, we are getting like n copies of n trajectory. Okay, n trajectories, each one of them. Ice trajectory is the following. So you have S step 1, 1, A1, 1, R1, 1. And in the second time step, you have S2, 1, A2, 1, R2, 1. All the way to SH, 1, AH1, RH1. Right. So these are state action rewards as you play this trajectory according to your login policy. So S1 is drawn from this D0 S. So this is so MDP is given by state space, action space, transition kernel, initial state distribution, and then the reward function, right? So this is the expected reward function, and then how the data is generated in the offline setting is by running the login policy, and I guess this A1H is drawn by taking the policy mil at S1 H, right? And then the reward RH1 is collected by drawing from the probability distribution of reward given S and action, right? So this is how the data is generated, and you have n trajectories IID, independent identically distributed. Okay, so the straightforward idea of importance sampling on this is to, well, like consider the entire trajectory a single data point and consider the sum of the total reward, like the reward of this problem, and then so you can write like naive IS importance sampling of target policy pi by reweighting every action, right? So first of all, this is average over trajectory, and secondly, I'm summing over all the reward H from 1 to H R I H, right? But I cannot just do that because I still have to reweight this. So I'm dividing the probability of taking this dividing the probability of observing everything, which you know, like according to the factorization of the joint distribution that we have seen, like the reward distribution and the state transition distribution, they are identical, right? So we will have we'll have D1 multiply with the transition P1, and then multiply with D1 and mu1 P1 and D2 mu2 P2, and then we don't have D is the initial distribution and take action and then transition to the next state. Once you have the next state, you take the next action according to the login policy and transition to the next one, and all the way this give you H minus 1, P H minus 1, and in the last step you have mu H, right? And on top you have D1 pi 1 P1 pi 2 P2, and everything got multiplied together, H minus 1 pi H, right? So everything that's not specific to the policy got canceled, right? So these got canceled out, these got canceled out. So at the end of the day, like this estimator becomes a weighted average of the cumulative reward and then product of rho at individual time step. H from 1 to H, where rho Hi is equal to pi AHI given SHI over mu AHI given SHI. Right? Does this make sense? So this is a importance weight of taking taking this action AH, and I'm reweighting the entire trajectory by taking the importance weight being the sequence of importance weight of everything, right? So naturally, when we take expectation of this estimator, it gives me the true value because I'm dividing the correct distribution and multiply also the correct distribution. Okay, so this can be slightly improved into the more standard importance sampling estimator, and in the Sutton-Bartle book, this is called per step importance sampling. So the idea is that well, I don't have to use the same importance weight for every time step, right? I can do the importance weighting because the reward that I got at time H is only like has nothing to do with action that I take after step H, because I have already collected that intermediate reward. So the per step importance sampling is essentially that I'm first like summing over H, and for every time step, so let's do the importance weighting for only that immediate reward that you receive at step H. You have 1 over n, sum over I from 1 to n, and product of H from 1 to let's do T to 1, T from 1 to H, and rho T, so this will be your per step importance weight and multiply with R H of I. Okay, making sense, right? So I can exchange the order and those policies and actions that I take after step H that has nothing to do with the rewards I have already received at time H. Okay, so this will be the important sampling estimator that we'll consider for the remainder of the lecture. Yeah, I'll leave the infinite horizon version of the important sampling estimator and the weighted important sampling version as an exercise for you guys to work out. Yeah, and also like try working out the expectation of this. Yeah, give me a second. So let me close the door. I think there might be some like outdoor noises that you guys are hearing. All right, can you guys hear me better? So Xuandong, is the issue still there? Okay, good. Okay, next, let's consider the doubly robust version of OPE estimators in reinforcement learning. Okay, so this requires us to, well, first consider an alternative recursive form of the per step importance sampling estimator. So suppose we start with step 0 by defining this per step importance sampling to be the trivial estimator of 0, and then we can define the estimator for the next step recursively using this formula. So let's try. Suppose there are just 2 steps, and we suppose there are just 2 steps, then V2 V2 IS is equal to row 2 R2 plus, so in our case, gamma is equal to 1 because we're not doing the discounted version. So then the previous step would be row 1 R1 multiply with oh yeah, yes, yeah. Sorry, this is recursing backwards. So IS 1. Let's say that H is equal to 2. So this will be row 1 R1 plus plus row 1 multiply with row 2 of R2, since R2 is the last step, right? So by recursively rolling out this this formula from backwards to the first step, then you can construct this value function of the first step, like through running this Bellman equation like updates. Okay, so once we have this alternative form of the per step importance sampling, we can add a doubly robust version of it by adding adding a Q hat value estimator. Let's say that you have a regression estimator that gives you an arbitrary Q hat. Okay, so let's say let's say you have and also this v hat of ST is equal to simply taking this action AT at ST and then average out that action parameter in this Q hat, right? And then plugging into here. So this is a doubly robust construction, right? So you have this baseline, which is coming only from the regression estimator, and then you are using the importance sampling idea to estimate the bias of this V hat. So in this case, ST and AT are observed data, so they are sampled from the probability distribution in the denominator of this row T. So the expected value of the second term is the same as the negative of the bias for V hat ST. Therefore, when you do this doubly robust estimation, you'll end up getting the same unbiased estimator. Okay, so yeah, I have verbally talked about the proof of the unbiasedness of doubly robust estimator. It's pretty straightforward to work out yourself, so I won't spend the time in the lecture to do that. And the variance of the doubly robust estimator, like similarly, when you take this V hat to be simply 0 all the time, then you can get the variance of the per step importance sampling estimator accordingly using the same formula, follows from a Bellman equation of variance. So this is very similar to what you have worked on in homework 1. by recursively applying law of total variance. So in the homework, you only have to you only have to apply it once because it was in the infinite horizon case. So in the finite horizon case, so what you need to do is again to go is again to iteratively expand this W robust estimator by following the recursive construction and go from the very last step to the very first step, right? And then and then by defining these corner cases, right? So you can you'll end up getting this expression, which in every time you recursively call the expression for VT, you introduce a new factor of rho t, where this t is a step. Okay, so ultimately, when you unroll everything, you will have the value of the variance of the W robust estimator to be of the form of the summation of product of rho t summation over t from 1 to h, summation from h to h, and yeah, there's an expected value over the data that got over S and A that got passed into this rho t, and lastly, you will have the conditional variance of you have conditional variance of your transition into the next state plus the reward that you reward variance of the reward plus the future cumulative reward given this S and A, right? So that would be the estimator. That would be the variance that you got after you keep applying this this variance lemma and then just work out everything. So what I want to highlight is that in this variance term, there is actually a product of all these importance weights, right? So intuitively, so when we are using such importance sampling estimator, whether or not we use this baseline and then contrast the doubly robust estimator, there will be such a product of importance weight term. Let's say that the policy pi and mu, they are only a little bit different in every iteration, right? But when when the time horizon is h, the differences of the choices of the difference of the probability of target policy and the login policy for taking this action AT, like will amplify and will go compounded. So at the end of the day, this term, this importance weight can get exponentially large as h gets larger, right? Which since every trajectory is independent, right? So inside the summation, so this part are all IID, so they are in IID trajectory. So by the law of large number and by central limit theorem, we know that the variance of V hat pi is equal to 1 over n of the variance of this individual term that's inside here. But wait a minute, this importance weight that got applied here can actually make this very large, can actually make this variance exponentially large. Therefore, the variance of the estimator is also exponentially large. Okay, so that's one of the main challenges of doing in some sense model-free style offline policy evaluation in reinforcement learning, even in the tabular setting. Because if we do the standard Monte Carlo and the importance sampling, like whether or not we use W robust at all or not, then we will run into such exponential dependence on the horizon in the variance and also in the sample complexity of estimating this value. Okay, so let me give you an example to illustrate concretely illustrate this issue and then highlight that there could actually be ways to resolve this, and highlight that this sometimes is more of an artifact of how we are constructing the estimator rather than something hardness as intrinsic to the problem itself. Okay, so I'll use this example from Liu et al. 2018. The title of the paper is called "Breaking the Curse of Horizon," where they give this example. So let's say that I'm drawing the state space diagram of a say finite dimensional a finite horizon or infinite horizon Markov decision processes. So in total, there are well 11 states. So these states are connected by actions that can take you either clockwise or counterclockwise. Suppose you take suppose you take A to be 0, then that gives you the deterministic transition that goes clockwise. Suppose you take A to be 1, then it gives you a transition to the next state in a counterclockwise fashion. All right, so let's say that you start here. So this is your initial state. Let's say that the reward are say so you have R equals to 1 here, R equals to 0.5 here, and R equals to 10 here. Yeah, let's say that you have these rewards. And then now let me define the login policy. Let's say that the login policy will take, regardless of what the state is, we'll take we'll take probability rho. So rho is something between 0 and 1. Okay, so S is equal to 0 with probability rho and 1 with probability 1 minus rho. Okay, now let's consider the target policy. The target policy will take action 0 with probability 1 minus rho and 1 with probability rho. Okay. Yeah, actually, let's simplify the target policy a little bit. Let's say that the target policy will always be equal to 0. Okay, now let's say we set the horizon. We set the horizon to be 200. Okay, so this will be a large horizon. And what happens if we run the per step importance weighting algorithm of this? So V of IS of the target policy will be 1 over n. Let's say that we collect a bunch of trajectories, and then we'll do the importance weights, right? So depending on whether you get action equals to 0 or action equals to 1 from the login policy, you will have you'll have 0 importance weight or an importance weight of 1, right? So you will get so you'll get 1 over rho to the power of the number of times a I h is equal to 0 multiply with the reward that you collected at also sum over h from 1 to h, I from 1 to n. Number of times that AH is equal to 0 up to step AT is equal to 0 up to t smaller or equal to h. right? So this is exponent here, multiply with R H I, right? And then I'm summing over H, right? So why is this? So I'm basically taking the I'm basically taking the product, and since this since this is a product, is a pi of a given s over mu of a given s, and then I'm taking the product over h from 1 t to the 1 to h, and this value is either and this value is either 0 or 1. This value is either 0 or 1 over rho. So yeah, actually in this, like, yeah, I deliberately simplified the example, which happens to have make it slightly more complicated, because in this case, like, this importance weight can often be 0, and in some other cases it will be exponentially large, and it only and this is only non-zero when the sequence of action that this mu0 happens to be taken is all a equals to 0, and that happens with probability. That happens with probability rho to the power of rho to the power of h, which can get exponentially small. So in this example, a lot of these summand are actually 0, and in those cases when so let me rewrite this. So this is to the power of h, together with an indicator that a t ATI is equal to 0 for all t smaller than h, right? So you can see that in this example, sometimes you have an extremely large value that scales with 1 over rho to the power of h, and in other times you have values that are extremely small, right? Yeah, that's actually 0. So whenever your logging policy in the sequence of actions up to step h takes one action to be a equals to 1, then you get no information at all from that trajectory for that time step. So then, like, when you work out the variance here, it is clear that this is as large as this is proportional to order 1 over rho to the power of to the power of h. But if we take a step back and then look at the problem itself, right? So when the logging policy is taking such a random walk from A0, and when we are taking many steps of this random walk, then the marginal probability that the logging policy will visit every single one of these states are more or less the same, right? So there are only 11 states, and you are running like 200 steps of random walk. So with this transition probability, and with this probability of taking either go left or go right, you can actually work out precisely what the marginal distribution of the individual state visitation. Okay, you can work out the individual state visitation, and for the target policy, the marginal. So even though it is following a deterministic policy, which makes the importance weight either 0 or something that's extremely large, in this target policy, you're actually just going around this circle again and again and again, and the expected number of times that you go around the circle is really like 200 divided by 11, right? Modular the residual number of times, because each time this policy is wrong, like you follow exactly the same trajectory, So the number of times that you visit each state is the deterministic value, right? But if we marginalize over if we marginalize over horizon, and then also marginalize over over the if we marginalize over the many trajectories, that we can actually estimate every single one of these states from the logging policy alone, like quite accurately. We can we will end up getting like many samples from this state and from this state and from that state to ensure that despite the randomness in the immediate rewards, then we'll be able to estimate these non-zero expected reward value like quite accurately for every single state. Okay, so I hope this example illustrate the kind of structure that the standard importance sampling estimator isn't capturing. Okay, so the idea, so how to capture this information and then come up with a better estimator that doesn't depend exponentially on the time horizon is through the so-called marginalized importance sampling. So what we can do is instead of dealing with the product of the importance weight that's given to you by the entire trajectory up to step h, so maybe we can like directly estimate the marginal state distribution and then correct for the distribution shift accordingly, right? So similarly, since there are many times that you visit the same state, then under the logging policy, maybe we can replace this, which is a single observation, with something that's averaged over the many times that you visit state S. Right, so that should be an intuitive idea, and this gives us the so-called marginalized importance sampling, because we are marginalizing the various trajectories by incorporating its structures and then estimate the state state occupancy for the target policy, and then use that to reweight. So why should this be a reasonable thing to do? Like if d mu of S converges to dt of mu S, and dt pi of S, our estimator converges to d pi of S. In addition, r hat t of pi of S converges to r t of pi. So if this happens, then then we can see that when we take expectation over how the state is generated, this state is actually generated from dt mu of S, since this is a logging policy's state with occupancy measure. So in this case, is this a valid probability distribution? And since we are dealing with only step t, right? So this is the marginal probability that this logging policy will visit this particular state, and this got canceled out with the term in the denominator, and then we get the exact formula for the computing the value of the target policy pi. Right, so the question really boils down to how do we construct these estimators and how do we show that they converge to these population quantities sufficiently fast. Okay, so what are some ideas that we can use? So maybe let's first deal with this r hat of r hat t. So we can design an estimator by simple like importance sampling, since this is just one step, and then that is straightforward to do. So let's average over the trajectories. Let's fix the step t, and then collect all the rewards that you have gotten at step t whenever you visit this particular state. So this will be so r hat pi t s. So this will be say indicator. So I'm collecting the number of times that we are visiting this state. 1 over n s. So this is the number of times I visit this state at time t. indicator STI is equal to S, and then multiply with the reward that you actually get. So that will be Ri of T. Okay, what are we still missing? We're still missing the importance weight, because these data are collected by running the login policy, which requires us to simply take A I T given S over mu A I T given S, right? So that becomes the importance sampling estimator of R hat of pi. So how about the other two? Yeah, for d mu, for the state visitation of the login policy, this is straightforward. Basically, we can take 1 over n, so this is the total number of trajectories, and then average over the number of times that you actually visit the state. Right, so we can simply plug in, and by definition, we know that this is a good and more or less optimal estimator, like for this quantity. And like what makes it slightly more challenging is to estimate the off policy state action visitation, so state occupancy under the target policy. Right, so one idea that we can do is to average over the multiple visit to the same state by using the same old trajectory based importance weighting. Right, so check that we can say, so this is one of the ideas. So we can average over the trajectories, and then we can simply use a product of h from 1 to t of these importance weights in that trajectory as AIH. Right, so these are pi over mu A of S at those particular step H, and multiply with the indicator that that we actually hit this particular state, right? So you can so you can clearly see that yeah, so this is number of times that you visit this particular state at time t, right? So clearly this is an unbiased estimator, because we have seen that this importance weight, importance weight has an expected value that is sorry. So let me do something else. Yeah. So the idea is that, yeah, let's scrap this. The idea is that we can estimate this importance weight together, like using by just averaging them over the multiple trajectories, and we can just count the number of times that you run into state S at time t over all the trajectories that you got. And then since each time that you visit, you can use this product of this importance weight to construct an unbiased estimator. And if you visit this state many times, and you can take the average, and that gives you something better than using only that trajectory. Well, what is an issue of this approach? Like the issue really is that by doing this, you're not getting around with the exponential variance in the estimator that you construct. So notice that you can at most like see n times of visiting any state, but the importance weight in only one of these steps could be exponentially large, right? So even though this strictly improves over the standard importance sampling, it doesn't actually help you with overcoming the curse of horizon. Yeah, so this idea was actually discussed in a more generous setting in some in a recent paper. In a recent paper that use non-parametric way of estimating these importance weights in the function approximation case, and they showed that asymptotically at a really large n, when h is considered fixed and when the number of trajectories gets exponentially large, and this approach can actually be asymptotically efficient. So no other approaches can beat this in some sense. When you use doubly robust estimator together with this. But like for our purposes, we're considering the case when n is relatively small and h like is an important quantity, that e to the power of h is important, that we do not depend on that in any quantities of the sample complexity that we collect. Okay, so the second and better idea is to use the structure of the Markov decision processes by designing such recursive estimation. Okay, so recall that. So this is something that you've worked out in homework 1, right? So this is something that you've worked out in homework 1, and essentially this is saying that this is a recursive equation for the marginal state occupancy over time t. So you start with some state distribution, and then you multiply that with a transition kernel under this policy pi. Right. So this is a matrix vector product, and this is a transition kernel S prime given S under pi, and this is a d pi of S. And if you keep applying this, you mix in the infinite horizon case, but in the finite horizon case, every time step you have a different marginal distribution. Like if you can know the state transition, and you can start with D1, so that's the initial state distribution specified in the Markov decision process itself, and over the trajectories, we can easily estimate the initial distribution since every trajectory is independent. And then we can apply this recursive formula by plugging in the estimator for p hat and d hat throughout, and then this gives us an entire sequence of estimator for every single time step. Okay, so d hat 1 is equal to basically the number of times that you visit S 1 is equal to S, right? And then once you have this, you can plug it into some estimator of the transition kernel. And what we do with the transition kernel, we can also try estimating it just like the reward using importance sampling, right? So here's the idea. We will use the standard importance sampling, and then you count the number of times that you transition from st minus 1 to st to a particular pair, and this gives you like whenever this the number of times you visit st minus 1 is non-zero, and this always gives you an unbiased estimator of the transition kernel. Okay, idea is use the standard IS for just that one step. And similarly, I've already told you about this. You can use importance sampling to estimate the reward under a particular policy at every given state and every given time. Okay, so is the estimator clear? Yeah, so we are leveraging the dependence in the data itself to somehow construct more efficient estimator. That's the idea. So it can be shown that if we run this, the recursive estimator version of the marginalized importance sampling, then we can get a mean square error of this estimator of this form. So we will have this 1 over n leading factor, not surprisingly, but let's parse what's inside. So we have this expected value, and this expected value over the policy mu. So these are the induced distribution of the policy mu. and the random variable here are st and at, and st plus 1 and rt, right? So if we write it out more explicitly, this is a sum over this is a sum over a. This is a sum over all possible values of at and dt mu s, sum over all possible value of st, dt mu st multiplied with d pi st square and d mu st square, and this got cancelled with that one. And we will have this variance. So I'll keep all the variance term inside without multiplying it. And what is this quantity? So that is the that is a value function going into the future when you are starting with st plus 1, right? So you've seen such variances that naturally pops up from the Bellman equation of variances, and what I really want to say is that let's try making some simplifying assumptions to simplify this bound, so that we can be sure that there are no exponential dependence on the on the horizon h. So let's make an assumption that dt pi over dt mu for any s. Let's say that this is smaller than some like crude upper bound tau. Okay, let's also assume that for all t and all possible actions and all possible state, the two policies are not that different. So this is tau s, this is tau a, right? So let's make these crude assumptions. Like recall that in the previous example that we gave, this both this tau s and tau a, they're bounded. They're bounded by they're bounded by 1 over rho, and where rho is a constant. So whatever we get out of this additional assumption will make sense, because under the same assumption, then the standard importance sampling will suffer from exponential variance. Okay, so in this case, we can replace this quantity by bounding it with tau s square, and we can bound this quantity with tau a square. What remains is the the next thing to look at is that this term is a summation of the reward, since we're assuming that the expected reward is between 0 and 1, and then the variance of the reward is also say smaller than 1. Then the cumulative reward that you collect throughout the entire trajectory have to be smaller than something that is order h. Right, so no matter what, that the expected reward won't be larger than h, and the variance of such bounded random variable will be at most h squared. Right, think about something that's bounded, and the largest variance of any random variables defined on the bounded domain needs to be bounded by square of the size of that domain. So collecting all these together, we can get this is 1 over n. And there's additional summation over n. So you have 1h factor here. You have tau s square factor here. You have this is tau a, right? But it is inside this variance estimator. So the largest value of the whole thing, the entire random variable inside the variance, is smaller than tau a times h, right? So the variance will be bounded from above by tau a square h square. And this is h cubed over n tau s square tau a square, right? So we only have polynomial dependence in h rather than exponential dependence on h. In addition, so when we are making such assumptions, you can see that you can see that the dependence on the state space and the action space actually also goes away, which means that the same approach, if you do it carefully, it can be used to handle cases when the action space is infinitely large. Yeah, provided that you are only considering target policy that are like a constant away in every single action from the logging policy. Okay, so does it work? Yeah, so we tried it on a couple of examples, and it does work, and it beats the importance sampling. It beats the weighted importance sampling. It also beats the other ways that ignores the fact that this is a finite horizon problem. So this is a similar idea that tries to use marginalized importance sampling, but tries to reweight the reward based on the stationary state visitation rather than based on the per step importance weights, which turns out to be highly biased. And you can see that when we plot the root mean square error divided by square root of root mean square error divided by h, then as number of episodes gets larger, we see this clear like 1 over n curve for the MIS estimator, and all the others like haven't really entered their asymptotic regime. That the only exception is the direct method, and which we haven't talked about at all, but we will in the remainder of the lecture. But before that, let me highlight some of the challenges of the analysis and sketch out the ideas under which we derive this this error bounds for the MIS estimate. But before that, I wanted to make sure that everybody like is now okay with how the estimator works. Right. So how. All right. So no questions. I assume it is okay. So we are using the data to estimate d hat pi and d hat mu and r hat pi separately, and then construct this more dependent version of the importance weight estimator, and then plug them in, and then end up getting this importance sampling based estimator. Okay, and by this recursive formula, by keep multiplying the approximate version of the transition, we can get d hat of pi and the hat of mu, right? So there's this that I didn't specify, is basically by simple plugging. By noticing that with n trajectories at every time step t, then each time that you observe a particular state, and that's independent. Right, so by plugging that in and divide everything by n, then we can get the estimator for under the logging policy, right? And then that instantiated both this d hat pi and d hat mu and r hat pi, and that gives us the MIS estimator. Okay, so let me tell you a little bit on the interesting aspect of the analysis. So starting with the challenges. So first of all, the statistical analysis is a little bit challenging due to that. Even though we have independent trajectories, the data within each trajectories are not actually independent. They are like the subsequent state depends on the actions, the realized actions that was taken within that trajectory, and also whether it also depends on the outcome of the state in every step. So it is entirely possible that in this MDP, you branch out at the very beginning of the trajectory, and then you follow a sequence of highly correlated state transitions subsequently. So the state space, say from time t onwards, might be multiple blocks, right, might be completely correlated depending on the outcome of the second step. And secondly, since we're just doing important sampling-based estimators and condition on some states being visited, so recall this one, right? So we have this quantity, right? So this estimator only makes sense if the number of times that over the entire n trajectories you have visited this state st-1 at least once. Otherwise, like, you have to define this estimator differently, say by setting it to 0, and that creates bias. Right, so there's a little bit of bias similar to the kind of bias that we run into when analyzing the model-based approach in the last lecture. And the issue is just gotten like significantly more complicated here, because if we run into this situation that one of the states is not visited, and then all subsequent states in the future time steps that's coming from this particular state will be affected. Right, so the bias can potentially be amplified quite a bit due to the multi-step structure of the Markov decision processes. And lastly, since we're constructing the d hat estimator by d hat pi t is equal to p hat pi t and d hat pi t minus 1, so the error of this the error of d t minus 1 pi and the error of the state transition estimator, so both of them will keep getting compounded, right? So there will be a snowball effect as you keep running this recursive estimation from t equals to 1 to t equals to h. So ultimately, like, your like, it is still non-trivial. So even though this is an intuitive idea, it is still non-trivial to show that the error propagation is not an issue, and you will not run into situations where the estimator depends exponentially in h. Right, so despite the exponential compounding of the error, we wanted to show that the error that's in the finally estimated the state occupancy for the target policy is reasonably small. Okay, so now let me tell you the couple of ideas that we consider to address these challenges. So first of all, this is a reorganization of the data set that you collect, right? So you can think about the data set to be the trajectory 1 to trajectory n, right? Each one of these is S1, A1, R1, S2, A2, R2 to SH, AH, RH, and the last step will be S1N, A1N, R1N to SHN, AHN, RHN. Right. So the first idea is to actually vertically partition this data sets that you collect. Instead of looking at this as trajectories, you consider all these trajectories are running in parallel. And in every time step, you collect this vertical block of data. You call that the entire data set for h equals to 1. And then for the second time, you call h equals to 2, and all the way to h equals to h. What I argue is that when we have this vectorized view of the data collection, then we can then by conditioning on the data set that's already collected in the previous time step, previous step, say h equals to 2, then conditioning on h equal to 2, and then the data set in h equals to 3 becomes conditionally independent. So even though let's say that we take h equals to 2, the data points across the different trajectories, they are they're independent, but the S21 given the previous S, they're not actually independent. But if we condition on the previous previous time step, it has completely given us the number of times the previous state has been visited, and that defines the number of state transition like state transitions that are starting from a particular pair of state and action, and then conditioning on that NS and NSA number at each individual time t. So by conditioning on, and these can be calculated from from this vertically partitioned data set, and then the state transitions and this p hat, this indicator of S prime given S across the multiple trajectories, they become independent to each other. Okay, so without going into the details, I argue that the whole thing now becomes like a big vectorized martingale, and with this view, and it allows us to apply things like martingale version of the Hofstein's inequality and Bernstein's inequality, and to leverage this conditional independence to simplify the analysis quite a bit. And the second challenge is actually an interesting one. So how are we going to address this issue when some of those states are not visited at all with some non-trivial probability? So the idea is to construct a set of fictitious estimators. So notice that these are not real estimators. We cannot actually construct them and then compute them in practice. But the idea is that they're easy to work with, and also they're very similar to, we can bound the difference between these estimators to the actual estimator, the actual MIS estimators that we implement. So recall that we can decompose the value across the horizon and across the different state, and then apply this plug-in formula to get d hat and r hat. And in fact, if we do this, if we replace this with d hat and r hat, then this is equivalent to the MIS estimator. And the idea is to simply replace every single one of these with tilde, and these tilde estimators would end up depending on these estimators that are exactly the same as what you would have gotten with the MIS estimator when the number of times you visit this particular state as ST is sufficiently large. Right, so this is if you have worked out the homework 2, this is related to the absorbing MDP idea by creating something that's different, but eventually will be very similar to the reality. And the underlying idea is that when this NS, when the number of times you visit the current state is relatively small, and in particular when it is smaller than what you expected to visit, so this is n times the marginal state visitation, is the number of times that you expect that you're over the n trajectories you will visit this state. But if you are substantially smaller than that, if you are substantially smaller than that in this otherwise, then let's not use the actual estimator because its variance is too large, and then let's simply hypothetically plug in the ground truth. Like I said, we do not really have access to the true value. So this is only for the analysis purposes, for us to work with this fictitious estimator. And similarly for our important sampling estimator for the state transitions, we also do the same trick. So whenever this ST-1 is not visited that many times, in particular when it is not visited sufficiently relative to our expected value, then like we'll just plug in the true value. Right? So the fictitious estimators are better than the actual estimators. And it's also kind of nice because whenever the actual estimator will be expected to run into some issues due to a small random sized data, then we have the true value of the reward and true value of the state transition to save the estimators from running into some pathological cases. Okay, the benefit of the fictitious estimator, obviously, is that it is easier to work with. In fact, you can show that this V tilde, so even though V hat is not an unbiased estimator, this V tilde is indeed an unbiased estimator. And also for all the Bellman equations of variance and so on, that you can apply to those cases when things are well behaved, when you do not have a very small sample size for any state. So those like applies naturally to the fictitious estimators, but not directly to the actual estimator. Okay, so and by and the next step is to show that the fictitious estimator is actually very similar to the actual estimator by this concentration bound. So this is multiplicative Chernoff bound, which is a close cousin to the Hofstad's inequality that we have learned. So like I said in this course, I wanted you to not only understand what I'm covering in terms of reinforcement learning, but also to learn a couple of hammers and techniques for you to use for your future research. So this is one of them. So so recall that in Hofstad's inequality, you are bounding the differences between the expected value and the sampled value in terms of their absolute difference, additive distance. This one is multiplicative, so it bounds a gap between your actually observed value and your expectation with a multiplicative factor of 1 minus delta, right? So if you deviate away from your expectation by a little bit, then you can use Hofstad's inequality. But Hofstad's inequality fails when your expectation is actually very close to the boundary. So in this case, we are dealing with a binomial random variable, which is a sum of independent coin tosses, and with each with probability P of turning out to be a head, and you run this for n copies. And when the probability of hitting the head in this bias coin tosses is very close to 0, then like Hofstad's inequality becomes inapplicable, because you need to add a small epsilon, and that epsilon is on the order of in this case square root of n, and that could be way too large for it to be useful. And then multiplicative Chernoff bound is like a slightly easier to work with than Bernstein's inequality, which aims at achieving the same goal, which like in particular gives you a multiplicative factor. So we can apply this to our problem of estimating the number of times each state is visited. So this is n, say nst. So this is a number of times that state S is visited at time t over by running logging policy mu for n trajectories. Okay, so first of all, this is a binomial random variable, and the parameter of this binomial random variable is dt mu of S, right? And the number of times that you run this, since each trajectory is independent, is n, right? So this multiplicative Chernoff bound plugs right in, and what we can do is to apply this multiplicative Chernoff bound to show that as t is smaller than n times d t of mu of S, 1 minus delta is smaller than e to the power of minus delta square n dt mu S over 2. Okay, and And all we have to do is to apply this and take union bound for all t from 1 to h, and for all s in the state space for all these pairs. And so in total, these are h times s number of times we apply multiplicative Chernow bound. Since this has exponential tail, then we apply this union bound without incurring more than a logarithmic factor in h times s, right? So what this is saying that the with high probability, right? So the or rather probability of the fictitious estimator is not equal to is not equal to recall that this condition is the same as the condition that we get here when defining the fictitious estimator, right? Here and here, right? Suppose we apply this union over all states and all time step is not equal to MIS estimator is smaller than I guess h times s times e to the power of minus delta square n times the minimum over all s and t and the t mu of s. Okay, so provided that this logging policy is visiting every single state with like a small constant probability, and then like you don't need this n to be very large before this quantity converges to zero exponentially, right? So we can even choose this delta to be something like O2 to 1 over n, right? We can balance it out so that we get an arbitrarily small probability distribution that's say n to the power of 1 over n to the power minus 100, right? Without incurring additional logarithmic factor. So we can actually choose this multiplicative factor to be relatively small, right? So this shows that except for very rare cases, then we can analyze the fictitious version of the estimator that is easier to estimate than easier to analyze than the MIS. And the next challenge that I didn't cover is the challenge of like error propagation, and this requires some like detailed calculations involving repeated applications of Bellman equation of law of total variance, which decomposes the variance into the summation over h and the expected variance. So this is something that we've already seen in a bound. So we know what this is, and this is an expected value of this is a like a expected value of the sampled version of this like ratio of importance weight square. So remember that like we're summing over this sh, so we can replace this sum over sh with expected value, but then introduce another 1 over mu the mu of s. So this and that together gives us this d pi over d mu square term in the theorem. Right, but now this is different. This is instead of having the true value d, now we are having this this d theta factor. NSH on the other hand, NSH is equal to n times the d hat of sh, right? So you can see that 1ON factor is coming from here. And then we're dividing this by this empirically observed state visitation under the under the login policy, right? So it remains to deal with this expectation and show that this is smaller than maybe some one plus a small value multiply with d pi over s square. Yeah, if we can show this, then that completes the proof of the theorem. Yeah, so this is an empirical, an offline version of the Bellman equation of variance with for the fictitious estimator. And then what we can do is to really use the fact that we can handle these failure cases relatively well. So when this happens, when this happens, we can replace this with something that depends on the population quantity already, right? So which and then what remains is a numerator, and using the formula of ex squared is equal to variance x squared minus plus the ex bracket square. So this is the definition. This is the definition of variance, and we can replace this with the summation of what we want. So notice that this d tilde pi is unbiased. This is unbiased due to our fictitious construction, fictitious estimator construction. So this is exactly what we want. So there's one remaining term to be bounded. So that's a variance of this d tilde h pi term. And how do we bound this? Like, this gets slightly more complicated, but the idea is relatively simple. It's still to apply recursively apply the law of total variances, but now this time you apply the vectorized version of the law of total variance by decomposing the covariance of dh as an entire vector. So this is in R to the S. So you can decompose this into expected value of variance and then the plus the variance of expectation, and then recursively plugging in the next round of covariance into this, and then you can roll it out. Yeah, so it gets somewhat complicated, and for those who are interested in this, I encourage you to look at the paper itself. But once we do that, we can use some crude bound to control the variance, and then show that it can also be bounded in the multiplicative factor that's proportional to what we want. So this is d pi over n. And if we look at the error propagation, so as h gets larger, this is not really something that gets worse, gets larger exponentially, but rather it depends linearly in h. Okay, so that's a full proof sketch for how we can get this. So once we have this, we can substitute this into here, and then into and then substitute the whole thing into this calculation, which gives us a variance of the fictitious estimator. And then using the fact that the fictitious estimator is very similar to MIS, then we essentially got the same bound to hold for MIS. Okay, so the question is whether this is the optimal thing to do. Yeah, let's take a 4 minutes break, and then we'll come back and then just spend another 10 minutes to wrap up the lecture. So we'll resume the lecture at 2:37. All right, everybody, let's resume the lecture. So we'll spend another 10 minutes also, like wrapping up the today's topic. So we've just worked out the proof sketch for analyzing the IMIS estimator, and the question is whether it is optimal. So the answer really depends on the settings. So in a full tabular setting, so when the finite horizon finite action, then we know that it is not optimal, and this is what the next slide is about. And in the case that remember that in MIS we are using importance sampling for estimating the state transitions and also estimating the expected reward under the target policy. So both of them are importance sampling based estimator. We know that when we have a realizability, then the importance sampling based estimator is typically not optimal asymptotically, as we discussed last time. So we do conjecture that in the infinite action case, like the MIS is with importance sampling estimators are actually cannot be improved. But if we have a realizability realizable regression function or have finite actions, then it shouldn't be optimal. So that motivated us to consider the tabular version of the MIS. So it is still the same equation, right? So it is still the same importance weighting, but we will now instantiate this d hat D hat and R hat using a different approach, right? So the like it is very simple. So instead of having this pi over mu, which we use importance sampling for, the only change the only change is to replace this mu with mu hat, right? So by replacing the actual probability of taking those actions with the estimated probability of taking those actions that are actually observed in the data. So this creates like we've seen that this becomes equivalent to just estimating these quantities using a model-based plugin. Yeah. And equivalent to plugin model-based approach. So how would we do the direct method in reinforcement learning in the first place? So that's one of the things that we covered for the bandits, but not for RL. So the idea is to, so in the model-based approach, let's use whatever data that you collect. This is a data of n trajectories sampled by executing policy mu. Then we can get MDP M hat. Right, so the M hat is the same state space action space, but the transition kernel is now transition kernel P hat, and the reward is a reward hat, and the initial state distribution is a D0 hat. Right, so you estimate this and then you plug in the target policy, right? By running this, so by plugging the target policy, and then you can, for instance, use value iteration. By simulating the Bellman equations for this empirical MDP, and then you can get say v hat and pi, and also by the first principle definition of what this mean. So this is what we call the little v pi hat. By definition, this is equal to the expected value of running this policy pi and R1 to plus R2 plus RH. The superscript indicates the data point, the first data point that you collect by running this policy. Running this policy pipe. And this could also be decomposed into the summation over H D hat d hat 0 s, yeah, summation over s, and then the v 1 hat s, and you can decompose it into state action visitation as well, using the h hat of pi plus v plus r hat pi of s. Okay, so that will be the version of the DM in RL that we run. So if we have this synthetic estimated MDP, then we can do whatever we want. We can run value iteration, we can run iterative policy evaluation, we can solve the linear system of equation like recursively backwards, since this is finite horizon, to get the to get the value estimate. Yeah, we can get the Q function and then V function for any target policy. Okay, so the tabular version of MIS is actually equal to like identical to the direct method that we talk about. So why is that the case? So let's quickly sketch it out. So as we've derived, so this is the definition of the TI-MIS and R hat pi T S P I, right? So this is the definition of MIS. So notice that a lot of these STIs they're corresponding to the same S. So we can exchange the order of the summation by grouping all those STI that at the same time point that happens to be the same state together. We can sum over S in the state space, and then have 1 over N. I guess T from 1 to H. So we'll have all these. We'll have all these again. This is mu and R hat S pi and sorry, this is R hat of S I at time step T, and the only difference is that we can now add an indicator is equal to S, right? And notice that when these are equal to S, we can replace all these with S. Then they are no longer they're no longer a function of they're no longer the function of I, right? So we can substitute this this S in here and replace this just with S. I'll replace this just with S. So this is RT, right? So they are all still a function of T, but independent to N, right? So that's why we can simply drop the summation. We can simply get rid of these altogether, because none of that is now none of that except this quantity is independent to is depending on N. So we can drop this from the beginning and then put this summation of I from 1 to N over here, right? Because all of this like is not indexed by I, right? So then what we can get is to further like put this thing over to the right hand side. So I'll sum over T from 1 to H D hat pi T S R hat T of S, and we'll have 1 over N, 1 to N indicator STI is equal to S, and over D hat mu T of S. But this is the same as that. So these two are identical, right? This is how we are doing the plugin estimator of the state visitation under the logging policy mu. So these two got canceled out, and then we recover the same quantity as we got in the previous previous slide. So this is a V hat direct method or model-based approach. Right. So you can see that the TMS is equivalent to a completely model-based approach, like when we go to the full tabular version of MIS. And I guess I still haven't told you that these two are also they would match up, but you can clearly see this. So d hat of 1 of S is independent to the target policy, and what we use to do this is to plug in, right? And when you simulate when you simulate the estimated Markov decision processes, you are using the estimated state transitions to roll out, right? And which says that d hat 2 S is equal to this pi hat d hat 1 S sum over S, right? So this matrix multiplication that we consider as the estimated version in TMIS is actually an exact transition dynamics in the estimated MDP, right? So this demonstrates that the MIS TMIS estimator is actually identical to a model-based approach, and so using a similar approach, we can work out the error for the tabular version of MIS, and you can see that the only difference is that now this term is outside the variance. So you can see that this is expected variance of expected over A, variance over S prime. So previously we had the variance of pi over mu. Previously we have we had the variance of this this whole thing in the place of this quantity. So clearly the by law of total expectation, you can decompose this into the expected variance plus the variance of expectation, and the improvement from the non-tabular MS, the tabular MS is that now you can completely get rid of this variance of expectation term. Yeah, another cool thing to see is that so if we make the same assumption about the bounded importance ratio, yeah, if we make the same assumption of bounded importance ratio, so this is bounded by dh pi times t of A, and this is bounded by pi a s multiplied with tau, yeah, this is tau s and tau A. Recall tau s and tau A, they are the upper bound of the importance weights of the state and the corresponding action according to the two different policies. Then we can completely get rid of this term, and then everything becomes the quantity of the summation of the expected conditional variance term, and it turns out that so this is the exact term that after we have extracted out the largest factor of the importance weight, and we can see that this term together with the variance of expectation is actually equal to the variance of the on-policy evaluation. Yeah, suppose we just use Monte Carlo and roll out, and now we're actually running this policy pi, and we can run this for n times, then 1 over n variance of pi summation of RT. So this will be the variance that you got. So we can see that using a model-based approach and by leveraging the Bellman equations and the structure of the MDP, you can even improve over the on-policy evaluation. So this applies even if pi is equal to mu. Yeah, another thing is that it is obvious from the left-hand side that since the cumulative reward is bounded and the whole thing, this is smaller than the whole thing is smaller than h squared. And notice that we're summing over h quantities. So each one of these summed can be h squared. So we're summing over h quantity of h squared, but the total variance after summing up the sum of expected variance is upper bounded by something that's order h squared. Okay, so from MS to TMS, if we further improves from h cubed over n tau a tau s to h squared tau a tau s over n. So which could be quite substantial. All right, so I will stop here, and in the next lecture we'll talk about fitted Q-learning, and we'll also talk about the uniform version of the offline evaluation, which bridges the gap between off-policy evaluation on one fixed policy to off-policy evaluation on all policy and the policy optimization problem. Right, so we'll talk about more offline reinforcement learning in the next lecture. And see you guys on Wednesday.